If you're into fitness, you've probably heard of VO2 Max before and how it's the alleged gold standard of running. But chances are, if you clicked on this video, you only know it as aerobic capacity, or how much oxygen your lungs can take in, or how much oxygen your muscles can use, or maybe this is even your first time hearing about it. But I'll tell you right now that there's actually way more to VO2 Max than you think. The reason it's considered the gold standard is because it's the ultimate link between exercise intensity, calories, and the heart. So I plan to make way more future videos on this, but today I'll just introduce you to the tip of the iceberg, which is what is VO2 max. This has everything to do with metabolism and calories, so we're taking it straight from the top. In my last video, we covered how hormones affect exercise and the adaptive homeostasis that comes with it. And now we're kind of moving towards the energy aspect of adaptive homeostasis. So this exercise physiology series is for anyone who wants to learn more about exercise and the human body. And I plan on explaining things in a very simple way. My last video was kind of long, but I plan on making things more concise this time and probably spreading things throughout more videos. So let's start with metabolism. Metabolism is the series of chemical reactions that turn food into energy and energy into use. So when people think about metabolism, they usually only remember digestion, but it's a chain of reactions. So you got your fancy steak dinner down there and you eat it and your body digests it into nutrients, and then your cells absorb those nutrients to make energy, and they use that energy to do stuff such as soccer and just keeping you alive. All of these are unique metabolic processes on their own, but they're part of the overall metabolism chain. And they can be sorted into two categories: catabolism and anabolism. Catabolism is the breakdown of complex molecules into simpler ones, which releases energy. For example, digestion. Your digestive system breaking down your fancy steak dinner into amino acids releases energy and is catabolic. But anabolism is the opposite. It's the building up of simpler molecules into complex ones, and that costs energy. For example, when your body stores fat, it uses energy to build up the free fatty acids into adipose tissue. Now let's move towards calories, which goes hand in hand with cellular respiration. Cellular respiration is a catabolic process in the overall metabolism chain, and it's the most important of them all, because this is the part where cells convert nutrients into energy. Basically, without cellular respiration, none of the food you eat would actually translate into energy, and you'd pretty much be eating for no reason. So there are many different pathways for cellular respiration in the body. Some use free fatty acids, others use glucose, etc. But they all fit under two main categories: anaerobic respiration and aerobic respiration. Anaerobic respiration doesn't use oxygen, while aerobic respiration does. Generally, your body relies much more on aerobic pathways because while they don't generate energy as fast as the anaerobic pathways, they're much more efficient. By the way, this is basically why you breathe, so that oxygen can be used in aerobic metabolism. So the general chemical formula for aerobic respiration is right here. As you can see, nutrients are turned into chemical energy by the cells using oxygen. This also produces the waste products of carbon dioxide and water, and some energy is always inevitably lost as heat. So what does calories have to do with any of this? From a chemical standpoint, a calorie is a unit of energy that raises the temperature of 1 gram of water by 1 degree Celsius, blah blah blah. So it's a unit of energy, and it's used to measure how much energy cellular respiration produces, and therefore energy expenditure, aka how much energy you burn. Because all metabolic processes are linked, so the whole reason your body produces energy is to burn it to do stuff. This is also why you see calorie labels on your food nutrition facts, because it goes as far back as digesting your fancy steak dinner. Well, knowing this is useful and all, but how do you measure calories? How can you quantify energy? Like, you can't just sit there and magically know how many calories you're burning every second. So there's two ways scientists do this: direct calorimetry and indirect calorimetry. Direct calorimetry is the measure of caloric expenditure by putting someone in a chamber that directly measures heat production from cellular respiration. Remember, some chemical energy is always lost as heat that you can't really help it. So scientists use that temperature change to calculate how many calories aren't lost, and that's how much energy you spend. Now, indirect calorimetry is the measure of oxygen consumption to estimate caloric expenditure. So this is only applicable to aerobic metabolism, which uses oxygen, as you can see from the equation down there. And for every 1 liter of oxygen that the body uses, about 5 kilocalories are produced and spent. So this brings us to a concept called VO2. Also, I'll definitely be making my next few videos on cellular respiration and energy, as there are so many concepts to go over regarding those, but these were the basics right here. Now let's talk about about VO2. It's honestly not unlikely that you've heard of VO2 max but have never heard of VO2 itself before. VO2 is the rate at which oxygen is used by the human body, so it's a metric for indirect calorimetry. And it's a lot different than just how much oxygen your lungs breathe in, because it actually represents how much of that oxygen all your cells in your body use for aerobic metabolism. So it can be represented as the inspired oxygen minus the expired oxygen, because no matter how much air your lungs take in, all the extra unused oxygen is always breathed out. So VO2 is essentially an estimated measure of energy through indirect calorimetry, but it's only applicable to aerobic metabolism and can be converted to calories and vice versa. And there are two different measurements of VO2, absolute VO2 and relative VO2. Now, absolute VO2 is basically the face value of how much oxygen your body uses as a whole, while relative VO2 is the same thing but per mass. This is because the more cells a person has, the more oxygen they'll use and the more calories they'll burn straight up, because they have more cells undergoing cellular respiration. For example, Shaq has a higher VO2 than Kevin Hart because he's like double his height. So relative VO2 takes the number of cells into account using mass and provides a standardized measure for VO2. The units for absolute VO2 are liters of oxygen per minute, while the units for relative VO2 are milliliters of oxygen per kilograms of body weight per minute. And as you probably know, everyone is burning calories at rest because cells are always using energy to maintain homeostasis and perform important life functions such as breathing. So on average, people have a relative VO2 of around 3.5 milliliters per kilogram per minute at rest. This is known as basal metabolic rate, or 1 MET, and it basically represents how much energy you burn at rest. It's important to note though that 1 MET is just the average. Some people burn more and others burn less, and you don't really need to worry about anaerobic respiration at rest because, like I said earlier, your body prefers aerobic respiration when it's able to meet energy demands, which is very low at rest. So VO2 and calories are both units of energy expenditure. Now let's practice converting them. As a reminder, 1 liter of oxygen is equivalent to 5 kilocalories. And it's important to note that a kilocalorie is equivalent to 1,000 calories with the lowercase c, which is what I talked about when I introduced that definition of raising 1 gram of water by 1 degree Celsius. That's the lowercase c. But 1,000 calories with the lowercase c is actually equivalent to 1 calorie with the uppercase c, which is what you see on the nutrition facts of your food. For example, there's like 400 uppercase calories in a pack of Shin ramen. So that's actually equivalent to 400,000 real calories. Now, I don't know why it's set up like this. Maybe brands are trying to market their food as less unhealthy than they actually are. But just remember that whenever you read nutrition facts, the uppercase calories are actually kilocalories. So how many calories do you burn a day just by existing? Let's start off with the basal metabolic rate, which is 3.5 milliliters per kilograms per minute, and then convert from milliliters to liters and liters to kilocalories, and then you get around 0.0175 kilocalories per kilograms of body weight per minute, and then convert minutes to days, and you burn 25.2 uppercase calories multiplied by whatever your body weight is in kilograms in 1 day, just by existing. So to put it into perspective, let's apply this to Bob, who weighs 150 pounds, which is about 68 kilograms. So 25.2 times 68, and Bob burns 1,713.6 uppercase calories a day just by existing. That's pretty crazy. So anyway, on a functional level, VO2 is influenced by two main things: the rate at which the heart pumps blood around the bloodstream, aka cardiac output, and how much oxygen cells absorb from the bloodstream. This is represented by Fick's equation, which states that VO2 is the product of cardiac output and the difference between oxygen concentration in the arteries and veins, which represents the amount of oxygen absorbed into the cell. That's what CaO2 and CVO2 mean, by the way. As I said in my previous video, the circulatory system is the one responsible for bringing nutrients and oxygen and stuff around and into the cells through the blood. So this is the link between energy and the heart. This brings us to VO2 max, where we must examine VO2 during exercise. So during exercise, VO2 increases with the intensity of exercise, aka how much effort you put in. This is the link between energy and exercise intensity. Basically, your body needs more energy the more effort you put in, and it increases aerobic respiration to meet these energy demands. But it's important to note that VO2 doesn't capture all the energy expenditure during workouts. This is because of a lag in oxygen uptake at the the beginning of exercise, known as oxygen deficit. Scientists don't really know why this happens, but basically the body is really bad at increasing oxygen use at the start of exercise, so it relies on anaerobic pathways instead. And also, if you increase exercise intensity past a certain point, aerobic pathways won't be able to keep up as well, because while they are the most efficient, they aren't that fast. So past a certain intensity, the body begins crossing over to anaerobic metabolism. This point is known as anaerobic threshold, aka lactate threshold. And as you know, VO2 can't really measure how much energy is expended during anaerobic respiration because it doesn't use oxygen, so there's kind of a gap there. I'll definitely go way more in depth on this when I cover energy in more detail, so stay tuned. But in this graph below, you can see VO2 as a function of time during a workout. Exercise seems to start at 2 minutes and it's at a constant intensity requiring an energy equivalent of around 35 milliliters per kilograms per minute. So it takes a while for VO2 to warm up to that value from rest, creating an oxygen deficit, which is highlighted in gray. But after it reaches it, it doesn't really change with respect to time much. And then exercise seems to stop at 10 minutes. But instead of immediately going back to 1 MET, VO2 gradually decreases. This happens in order to make up for that initial oxygen deficit and is known as EPOC, which I'll cover in another video. But that's essentially why you're out of breath right after running, and so you still breathe heavy to make up for that oxygen deficit in the beginning. So VO2 steadily decreases, but at a point of very high intensity, it can't increase anymore and plateaus, as shown by this graph comparing VO2 to intensity. This plateau is called VO2 max, and at this point, VO2 can't increase anymore because your body isn't able to use oxygen fast enough to keep up with further energy demands, and so your body fully relies on anaerobic pathways to supply all additional energy. These values on the graph are all made up, by the way, and they'd be different for everyone. So VO2 max is the maximum rate at which oxygen can be used by your body during exercise, and it defines your aerobic ceiling. So while VO2 is a metric for energy, it's also a metric for exercise intensity, usually referenced as a percentage of VO2 max. As for what causes VO2 max to be a certain value, we have to look at Fick's equation again. VO2 max is essentially the product of your maximum cardiac output and the maximum amount of oxygen your cells are able to extract out of the blood. And by the way, cardiac output is a product of stroke volume, which is how much blood the heart pumps per beat, and heart rate, which is the number of heartbeats per minute. So your maximum heart rate and stroke volume both play a big role in determining your VO2 max. This is why cardiovascular endurance is so important for exercise. So now we know what VO2 max is, but why is it so important? First off, it's a metric for aerobic exercise performance, such as running or cycling, because it's the maximum intensity at which aerobic metabolism can meet energy demands. It's also an indicator of cell metabolic health, because it's also determined by how much oxygen your cells can extract from the blood. And it's also determined by cardiac output, so it represents the efficiency of your cardiovascular system as well. Additionally, it's a big indicator of longevity because of these two factors. So generally, the stronger your heart and better your metabolic health are, the longer you'll live. Let's also talk about some common myths about VO2 max. You'll definitely hear somewhere that it's the deal breaker for long distance exercise. This simply isn't true, because while it is a really good metric, there's also other stuff like running economy and lactate threshold and etc. Running economy is basically how much effort you can give at a specific percentage of your VO2 max. Remember that graph I showed earlier comparing VO2 to exercise intensity? Like I said, those values differ for everyone, and some people can put more effort in without needing as much oxygen. This is why two people can be running at the exact same speed and one's just chilling while the other one looks like they're running for dear life. And I also mentioned lactate threshold earlier. That's the percentage of VO2 max in which the body starts switching over to anaerobic metabolism. So generally, the higher your lactate threshold is, the more effort you can put in during exercise while still fully relying on aerobic metabolism. Another myth is that VO2 max is fully determined by genetics and you can't change it. This is just simply not true, as cardiac output and how much blood oxygen your cells can absorb can actually be greatly improved with training. Another myth is that VO2 max is only relevant to athletes. This is also just false, because like I said, VO2 max is a massive indicator of longevity because it reflects cardiovascular and metabolic health. So VO2 max is cool and useful and all, and that's great, but how can you find your VO2 max? The short answer is that you can't do it yourself. You need laboratory tests where you exercise on a bike or treadmill and scientists hook you up to a metabolic cart, which is like the breathing apparatus to measure how much air you inhale and exhale, which is how they get your oxygen values. Another way, which I guess you can do yourself, is to use apps that estimate your VO2 max during exercise based on heart rate and info such as weight and age. But keep in mind that this is only an estimate and not really accurate. So that's pretty much all I got for today. Basically, VO2 max, super important, ties together energy, the heart, and exercise intensity. And I know I went probably a lot faster this video, and I try to keep it more concise than last video, but I'll definitely be making more videos on concepts that I mentioned, such as anaerobic respiration, aerobic respiration, lactate threshold, epoch. Basically, we're moving gears towards energy. So in my last video, we started off with hormones, and I plan to go around and end off with the step-by-step responses to exercise, so basically everything put together. So once again, I'll definitely have resources down in the description to help you better understand VO2 max and calories, and if you still have any questions, feel free to leave them in the comments where I'll try my best to respond. So definitely stay tuned. I hope you enjoyed this video and learned a lot. Peace.